Okay, so I was trying to see if I could compile 16-bit real mode code only using the C compiler, at least for the build step. I know this will still call like the C preprocessor to preprocess things, or the GNU assembler AS or some other assembler to assemble the things, but if I don't have to explicitly put that in like my build process or makefile, what have you, then it would be a little bit easier, at least for dependencies, like for a bare metal OS project or bootloader or something, to only say, hey, you can just use a C compiler by itself, albeit with GNU extensions most likely. So that's what I tried to do here. I found an article I read several years back that I didn't understand, and I did understand it today. I don't remember it off the top of my head. It'll be in the description somewhere. But it showed that, hey, you can use the -M16 flag, among other things, to generate 16-bit real mode compliant code, at least for a 386 and above for x86. So you'll see that it generates 16-bit code, although it generates it with 32-bit address or data size prefix bytes. So it works on only the 386 and above, not the 286, because it'll use things like ESP or EBX. The extended versions, which have prefix bytes for 66 or 67 in the generated assembly. But other than that, and the subsequent code bloating as a result of that, it does seem to work all right. So I have a small example here for a boot sector that doesn't do anything but loads from the disk. And I'm using inline assembly, which is technically not in the C standard either, so it's not fully ISO C compliant, but I do at least have tried to do a minimal amount of GCC or compiler extensions for this. So reading the disk sectors with int13, that works. So I'm just making a disk image for like a floppy, we'll say 1.44 megs. The boot sector is loaded at 7C00. I'm reading sectors right after that point. So I'm reading from sector 2, 8K, 16 sectors to 7E00, which I put a small second stage that prints a string, and that loads a sample GDT, jumps to a 32-bit mode, jumps to a kernel, which all it does is print a string, just to prove that we can print and work in 16 and 32-bit mode. But the boot sector here, all I'm doing is reading the disk sectors and jumping to memory here, just void, passing it nothing. I am trying out C23 if things look a little odd. The entry point here, I'm setting a specific section for text.boot, and I'm going to link that into the start of the text section every time, so that the code runs here for the entry point instead of whatever the linker might want to put the entry point at in the generated executable, like the ELF file or the portable executable format. I'm saying, hey, I want to link this first, and I want to run this first, and that'll be in a linker script. The naked function says that I can only put assembly in here, only inline assembly. And I'm doing this separately from my main that I'm jumping to, just to show that you can separate them out if you want, and you can reference symbols in the assembly, although that may not be a best case that you want to do that all the time, and it may be that this has to be after this point in the generated translation unit, but in this case it works for a very simple boot sector. 512 bytes, we're just jumping to main, loading sectors, and jumping again to other memory. But generally I want to use volatile and a memory constraint just to be extra sure that it's not moving the inline assembly around. You don't need volatile if you don't have output parameters, for example, but I like being extra sure. The final output that I should have shown, but I didn't, the final output I'm showing is just printing text strings for 16-bit real mode and 32-bit protected mode in each of those things, and then I have a final sort of sentinel value at the end to prove that I'm halting and nothing's going on, which the monitor doesn't increase the text size, so that's all right. But that was the boot sector, as it were. How do I get this 512-byte boot sector made only in C? Well, using assembly, but anyway. I'm assuming ELF files for this portable executable might work a little bit differently for these manually created linker scripts, but the boot LD file here, I'm setting some program headers for the permissions for each of the sections in the ELF file, and I'm transforming the ELF into a flat binary, but I'll show that in the makefile in a bit. But read, execute, I'm setting those bits, or read write or read only for text data and read only data sections specifically. I'm loading the text section at 7C00 because that's where the BIOS loads a boot sector for 16-bit real mode. I'm keeping the text.boot section here, which is where my entry point was. I said explicitly put this section at .text.boot. I'm keeping it here. You may not need keep on your setup. I'm putting it there to be doubly sure that it doesn't move that around, and it says at text, put this first, and then put whatever rest of the text section or the code that's going to run is generated. I'm putting that within the program header with a loadable flag, so it's a loadable program header section, readable executable, putting that in there with the colon text, which references that text. Read-only data, I'm putting in read-only, data, I'm putting in data. BSS and comment, I'm putting after data in that data loadable section up there. So to put the boot signature that's required for x86 to count as like a bootable disk at byte 511 and 512, so byte 510 after 7C00, I'm putting 7DFE with just a name for a section, and I'm putting short, which is 2 bytes, and that 2 byte value, AA55, in Little Endian. And I'm discarding some sections that are put in ELF that may not be put in the final flat binary by default by the linker, but I'm just adding it here just in case. Relative or relocation, whatever rel stands for, I may need later depending on what I'm doing. Right now I didn't because I'm pure static linking these flat binaries. But the note and comments are superfluous and they're just for info, so I'm taking those out. You may have more or less things depending on what your stuff does. The stage 2 that this is loading here is going to print the 16-bit string, so I'll show that. So it's stage 2.c. I have some more BIOS interrupts that I'm calling with inline assembly. I'm not doing naked functions for these because I can just call them in C. It does put 32-bit stack operations, so it does make the code larger from the 66, 67 prefix bytes per instruction. And it has stuff for moving and setting up the stack frame and all, which you can take out with compiler flags or get around it in other ways if you want. For example, with passing parameters here to hide the cursor, or well, to set the cursor with X and Y, there is another compiler extension you can do, regparm and 1 to 3, and this will say, I want 1 to 3 parameters, depending on what you do, to be in registers instead of the stack. That can make code a little smaller, it can make it possibly faster, it depends what you're trying to do. Instead of offsetting from the stack pointer, that would instead move within A and BX, for example, or maybe if you set a different calling convention, it would do other registers. But that's one way to slightly get around some stack use if you want. But all I'm doing with these BIOS interrupts is mainly for the display. I'm clearing the screen by scrolling the window down, a full screen's width for the default text mode of 80 by 25. The colors I'm setting for that are going to be the black background and the light gray foreground, so that's what I'm printing the text colors as. I'm hiding the cursor by setting it as invisible in these bits here in CH. So that sets it to invisible cursor size along with the top and bottom lines for it. The cursor position I'm just going to set to 0, 0, but to set the position, it's doing this. And to print a string, I'm doing the AH0E teletype output, oring the lower 8 bytes for that character into AL for the AX register. And again, for a lot of these, well, maybe just that one, because I'm using a pointer, I'm setting the memory constraint here, along with volatile to make sure this is not moved around for loads and stores around this location that the compiler is gonna, or the assembler is gonna use and generate. To load the GDT and jump to the kernel, making sure these are packed, which I wish was just in the standard so I didn't have to do this vendor prefix nonsense, but whatever. That's still less code to type than _attribute, _packed, in parentheses, so. Just a plain GDT with 3 descriptors for null code and data, and a plain GDTR for 32-bit, which is 16-bit size, 32-bit addressing. The GDT I have initialized here, so you can use some niceties of C interacting with your inline assembly with designated initializers, compound literals, and the like. And that's nice to use. For the address here, it's not a pointer, so I have to cast the address into the plain 32-bit value from the pointer value there. You can use C variables or global variables, local variables, whatever, in here, for example, with a named parameter that I'm using, which is to general use intermediate or memory or register, whatever constraint here for input. For output, there's nothing, so again, technically I don't need the volatile, but I'm putting it there to be extra sure. But what I'm doing is loading the GDT, setting the paging bit here, doing a far jump to set the code segment, and then generating 32-bit code explicitly with the GNU AS directive.code32. I have a label to jump to for 32-bit code, setting the rest of the registers, setting the stack to some value, and then far jumping again, which technically I might not need the 8, but far jumping again to jump to the kernel here, which I'm loading and linking at 9000. I'm switching back to 16-bit, which for GCC is usually code 16 GCC, that's generated from the -M16 flag. For Clang, you might be able to get away with code 16, because I don't know what the GCC specific stuff this does is, but one thing the -m16 flag does is just put this at the top of the generated assembly, and that tells it to generate 16-bit code, but with the 32-bit address or data prefix bytes. So that's why that's working. I would like if Clang and GCC just either honored code 16 or had some other directive of saying don't use 32-bit prefix bytes if you can help it. That would be nice. But I can't get that to happen. If you want things to not do that, then you're going to have to write only naked functions with only 16-bit inline assembly. But if you don't want to do that, then you'll have to deal with some code bloat here and there. Regardless, if you are doing a freestanding and sort of bare metal project like I'm doing here, you do need to at least provide memset, memcopy, if not memmove, memcompare, to be able to use and access sort of good initialized values. Like here, designated initializers, compound literals, and the like. This is going to use something like memcopy to set these bytes, or memset if it's all zeros, for example. You do need these functions defined if they're not linked in elsewhere or otherwise. And giving a -f freestanding flag with no standard live for linking or no built-in, you're going to have to provide these so the compiler can use them and find where they're at. Okay, similarly to the boot sector, I'm linking stage 2 in a specific section because I'm doing flat binaries for this, and I'm linking that at the start of the text section. But this, again, in the order, should be the order in which the functions are laid out. Clearing the screen, hiding the cursor, setting it to the top left in text mode, and printing that string. Then loading the GDT, jumping to the kernel for 32-bit. So the second stage is pretty similar to the boot sector. I'm just linking at 7E instead of 7C, but the program headers are set up the same. The sections are set up the same. The difference is that I need some section here in order to properly align at the next sector boundary. So in the boot sector, I just set it at a given address. This one, I just want it wherever it ends to be at the next 512-byte boundary. If you do that without the -1 and you put a byte there, it'll be 513 bytes. So I'm subtracting 1 to make it 512. This says, hey, back up to 511 alignment, maybe, and then put a byte there for 512. Normally in assembly, well, I'm not used to GNU assembly, but normally I would do like times 512 minus the current position or address, program counter value, what have you. And then we'd define a bunch of bytes like to pad it out to the next 512. Or whatever. This wouldn't be 512. This would be whatever the current size is modulo, and then adding it back to align upward. But you know what I mean. GNU AS, if they don't have times, maybe it's repeater while, and it's like a byte instead of a dB. But it'd be somewhat similar. Instead of a dollar, it's a period, I think. Yeah. Anyway, that's how you pad out with the linker to the next sector boundary. Same discarded sections there. So the kernel is very small. That I'm jumping to in second stage, where I'm just going to 9,000 that I'm linking it to. I guess one other thing here, you need to reset back to 16-bit code generation if you move to 32-bit and you have other stuff in the translation unit or here in the file after this point, or else GCC at least is going to generate bad code. It'll expect this to be 32, even if down here it's supposed to be running in 16-bit. You don't want to do that. So reset this if you have more stuff that's going to be after this point in 32-bit mode, and you'll make sure you get around that, any issues for that. So the kernel's pretty small that I'm loading and linking here. I'm just printing a string, but I can use the actual full 32-bit address now with abandon because I'm fully in 32-bit mode at this point, so it's not going to be cut off or anything. We can use B8000 for the color text mode memory, and I can print a string there by just getting a pointer to that and offsetting for 2 bytes per character. So that's all this is doing. 80 characters per line, 2 bytes per character. Setting the colors again for black background and light gray foreground VGA. And similar to the others, linking in a section at the start of text, just printing that string at X0 and Y2, so row 2, but at the start of the line, printing that 32-bit code, halting the CPU with the Sentinel value here for everyone's favorite caffeinated bean juice. And the kernel, similarly to the others, setting the read-write execute flags for the program headers as needed. I have been setting the entry point here. This doesn't do anything for me, but get rid of a warning that it can't find _start or it can't find entry, and it links at the start of the generated flat binary anyway. So this just gets around a warning, but Even if you do have this, it doesn't put the entry point you set at the start of text. That's why I keep having to make explicit sections here and put them there with keep. If you have issues and you don't have this and you have an entry point, you might just want to add specific sections here that you want to run. Guarantee will run first. Regardless, this is similar to the second stage in that we're just padding out to the next sector boundary and discarding stuff I might not want. I'm just linking it at 9,000 because Dragon Ball's a good meme and a good time. Okay, and just to recap, this prints, again, the 1632-bit code there. And that prints there. Okay, so how am I building this? With the makefile, I tried to make it basically as simple as I could and still fit on a single screen here. GCC or Clang, it builds with both. I could show that. If I can type, which I never can. It builds with both, it runs with both. Clang, I found, generates maybe sometimes some nicer, strict 16-bit code and doesn't put 32-bit register use as it can more often, but it's, you know, hit or miss depending on the compiler version and the day of the week, really. But for the flags, I'm saying, okay, I want pretty much ISO C compliance. Warn me about any errors here with pedantic and all in extra. I'm not doing optimization, so maybe this would catch other errors. I can check right quick. Do I have any issues here? Does it still work? Take out debug info. Does it still work if I compile with optimizing? It actually doesn't. It says we have symbols already defined, so I might need to mess with some stuff for that. Symbol set segments is defined. Okay, so that would be in stage 2 in the inline assembly. I can maybe fix that right here, because yes, this could be in different parts that it copies and moves around, so it already has the symbol referenced. I'm not sure if I can do a relevant symbol here, a relative symbol. Like if I do 1 and we do 1F, like does that work? I don't think that would work. But I'm not really sure. Okay, well maybe that would work. Alright, that'd be cool if that works. This is not in my script, so to speak here. Can you just go back and have me stop? Do I have any more jobs in the back? I don't. No more jobs in the background. I just want to make sure it possibly builds with both. Okay. So just use relative labels, if I went by that too fast because I'm scatterbrained. You can use relative labels here. This 1 is before this point, so 1F goes forward, finds that label. If it was behind, like back here, you could do 1B, and you could have multiple labels with the same name, and just wherever you use them, use B or F as needed. But that makes sense. So it might put this code in multiple spots before optimizing or converting it or moving it around later, so that makes sense. If it was already generated, it wouldn't work. There may be something in GNU AS to do to specify like a different local name, like with the % or something, I'm not sure, so that the label would be unique. I haven't run into it too much so far, but I'm not fully familiar with GNU assembler either. Regardless, fixing issues live, that's always fun. I'm setting the architecture to i386 because for the -m16 flag that I'm generating 16-bit code with, I need at least the 386. So that's why I'm doing that. For this, I'm doing a freestanding, no libc hosted implementation, although we still have some headers available like standard int that I have been using. I don't want position independence for this because I'm just doing some plain static linking at set addresses, and I want to ensure that those happen. For an actual project, and I had, you know, a more full functioning kernel, I would want to write a small program loader that is loaded by stage 2 or some other pre-kernel setup to where I wouldn't need NoPy for it, because it's easier to deal with relative addressing at that point in 32-bit mode. So this is just, I treat this for 16-bit mode that's very small only, but in a more full-featured setup, potentially second stage, or at least the kernel, would be position independent. No stack protector gets rid of some errors for a stack check flag and stuff that needs to be defined, at least for Clang. And I don't want canary values, and I don't want built-in functions that are attempting to be put into my binary. So even though this could lead to buggier code, it needs to build to begin with, so I'm using that. No built-in, I'm making sure we're not getting built-in headers or libraries or things, just in case. I don't remember exactly what no built-in is, but I did need it. As opposed to no standard live, which says don't link in the standard C runtime startup and other files. But this might just be for compile time, and this is for linking, and they do similar things. But anyway, no asynchronous unwind tables I need because GCC likes to generate frame and or frame header sections, and I don't have things to process or use those, and I don't need exception handling. In my mind, exceptions and interrupts are going to be handled later for like an OS dev project that this might be. So I'm going to handle those in my code. I don't need them in there to begin with when they don't work, especially. So I'm getting rid of that with this compiler flag here. There's also a linker flag for maybe no generate. This is not correct. No generate frame. There's a linker flag for it too. Don't remember exactly what it is. Let's say Yeah, no frame header, so you can do that. There's also an frame section to begin with, though. But anyway, for the common linker flags, I'm saying don't link in the standard lib. Why is it with here and here? I don't know, but it works for both. I needed it for the compiler flag to not mention or not use C runtime and startup things in addition to the standard lib, the object files. And I do need it when linking to say, well, still don't link in those things I don't want. I'm using static linking only, not dynamic. You could do static pi or something for like the kernel later if you want, but for all my code right here, I want to make sure everything I'm typing in is included and I'm not using any dynamic shared libraries or objects for this. Omagic says don't 4K or don't page align the text section and make sure it's not only read-only. Or maybe it's for any section actually. Let me make sure. Don't page align data, rather. And don't make text read-only. So I've seen nmagic online, which is page align data, or maybe just don't make it read-only. We can just look at magic. There we go. There's qmagic. Ooh, it's ignored. nmagic is don't page align. Omagic also makes text not read-only. I figured maybe adding that potentially could lead to optimizations for, say, code size, where it moves some data stuff into text if needed. You may be able to just get away with nmagic. It doesn't matter. I don't really know what they do other than that anyway, but it works for a small contrived example, of course, either way. Build ID, I got warnings about not providing a build ID, so I'm telling it not to give me one to begin with because I don't need it. And we're making the 1632-bit exes there. I'm making a disk image, just calling it disk.raw. If you're using it in qemu like this, don't include a space at the end or it'll give you errors because it's trying to use a disk and you're breaking the sort of parameters that you're sending to the drive option. So make sure there's no space there so that this, if you're using it as, a macro thing here, because otherwise there'd be a space and that breaks it. So I don't want that to happen. But I'm just building the disk image and running it for debugging. For qemu, we have a -S flag, which says stop until I'm continued elsewhere or otherwise. So qemu will stop operations until you tell it to start whenever you start running it. The -s says make a connection port for GDB on TCP port 1234. So I'm doing that, running it, which it'll run and then stop immediately until continued. And then I'm running GDB to then connect to QEMU and continue it. I have a .gdb init file that I'll show in a minute. So to make the 16-bit and 32-bit EXEs, I am using the gmake pattern matching because it's really nice. This should still work with POSIX because I don't think that really affects things. For this, yeah, it's still, make still runs the same. That doesn't really matter here. But this is gmake specific because it was easier to just copy paste this stuff for 16 to 32-bit. The only difference here is I'm doing -M16 for 16-bit code generation, -32-bit for 32-bit code generation. And specific linker flags, I am sending just to get the name to be specific. I'm putting them in here for this recipe, making the boot, the linker scripts specifically for the 16-bit, the boot in stage 2, and the kernel. And then I'm naming the elf with the .elf so that I can then do object copy, make that a flat binary with -o binary, strip out the debug info. I may not need to do this, but just in case, I'm going to remove debug info in case I compile with the -g flag. And I'm making that into the final plain named EXEs here. So for LD, for ELF files, not for portable executables, but for ELF files, there is another flag. You could set the output format specifically for binary on the command line, or in the linker script, it's output format binary. But for PE files, that doesn't work, and I want to keep the elf file here for debug info specifically, so that's why I'm doing that. Object copy works as well if you want to do like it's only copy debug it, something like that. I don't remember. There's only keep debug if you want to strip everything but debug info. There's decompress and compress. There's also add link. So if you run object copy to only keep the debug and maybe just make a separate symbol file, then you can strip the symbols from the original elf exe, we'll say, and then you can add a link from that elf to the debug symbol file to kind of keep them separate. So your regular elf executable can be smaller by not including the debug info, but you can also say that I have the debug info, it's just linked over here. Maybe that's closer to Windows with their PDB file set up. But the reason I'm doing this in 2 steps is to have a flat binary that I'm running, but if I want to debug, I want the symbols for that, and I need somewhere to get those symbols from, such as the elf file here. Or the object file, but the elf has the actual addresses after linking, so that's more useful. To make the disk image here, I'm just concatenating the 16-bit and the 32-bit ones together to some temporary files, making a 1.44 meg disk image out of 1440 1024 byte chunks of zeros. I'm putting the 16-bit files at the start of that, and then since they start at 7C00 for the boot sector, the kernel starts at 9000, so I'm just doing a plain sector offset into the disk here, which is not good. So I would want a better kernel setup to be able to put it at whatever address I want and to make it not position independent. So I would use probably pi for the kernel, and I'd have a different thing here where it doesn't have to be at some weird set offset, just because it's at a plain sector boundary. And in the boot sector, since I'm loading starting at 7E, I was just doing the same sector offset so that it worked in memory as it is on the disk and made it very simple for this contrived example. Regardless, this does work. No truncate means I don't shrink the image when I'm adding those bytes into it. So that's all I'm doing there. This is the same as 10, though, but I'm doing a calculation in case I was messing with it and I wanted to move the kernel somewhere else. You may see some other name files here that I'm not generating, and those are for if I want extra debug and linker info. So you can put a save-temps flag for the C flags here, and what that will do is generate, that will keep the temporary files that are generated during compilation, such as a preprocessed file, or a file to send to the preprocessor, the object file, the generated assembly, the boot.c, and Clang also generates a LOVM bitcode file. If I look at the file to send to the preprocessor, for example, this says that I think it's just saying different files that are going to be included. I need the line, if not the column and length from that line that I'm taking info from. I don't quite know what this is doing, but it's basically saying all of this info is going to be sent to the preprocessor to then be sent and compiled with your actual code at the bottom here. So it's just getting info from the headers that it'll then send to the preprocessor. But other than that, I don't really know what the format of that's supposed to be. But I can see with the -m16 flag that this is what's being put at the top of the generated assembly, the code 16 GCC directive. And that, among other things, will add these 32-bit registers, which will add the 66 and 67 hex prefixes, which is why the code's a lot larger. So I'm trying to keep this example to where the code doesn't go outside of 512 bytes for the boot sector, for example. But if you just want to write a naked function with 16-bit code, your boot sector can do a lot more. But if you only want to run and just load sectors and immediately go on to where the second stage can be, however big it needs to be with the code bloating, that's fine. But if you look at the bytes, you'll see, yeah, we have all these 66 and 67 prefixes and places for those 32-bit register use in the 16-bit real mode code. I can look a little bit about what sections were generated, if that's useful for debugging. So boot.o will have debug and have rel, so for, I think it means relative sections here, that says I want to move this stuff around or put it elsewhere. But the actual elf file does not. It does have the debug info, and I am stripping that with object copy when I make the final flat binary. But the final flat binary is just data. Well, this is a boot sector actually. That's why it looks a little different. But for stage 2, I can't tell. I guess the only reason file says that is because of the AA55 at the end of the 512 bytes, yeah. So the other thing that Clang would generate that I can't look at is the LOVM bit code, but I can at least show that it makes that with the save-temps. And Clang also doesn't like the GNU extension for the preprocessor file, even though Clang is the one that is using and generating this. Or possibly CPP is made for GCC on my system and not Clang, so Clang would use a different CPP, C preprocessor file that would be a better extension format, or not use those. I don't know. But Clang makes a BC file which I can't read. It's just it's plain binary for me. But that is a LOVM intermediate representation bitcode file. So if you have a reader, you can look at that. You can look at that for more info or more debugging, but the rest of this stuff will be pretty similar, although Clang doesn't put GCC on its 16-bit code directive. And Clang, I've found in a lot of places, kind of makes some smaller code. It does still use 32-bit registers, but sometimes it makes simpler code. So it depends, though. It's hit or miss whether Clang or the other will work for you, but I found Clang, I think, more often uses 16-bit registers where it can, at least for my setup here. So that's interesting. They are both the same at the end for me, though. At this point, I don't get code that's generated more than the same number sector boundaries for these things. It's 2 sectors for stage 2 at this moment, 1 for boot, and the kernel is also just a sector. Okay, the only other thing would be the map file, which I'm going to put in for the specific linker lines here so that they have the same name. We'll say the target.map, and I'll just do it for the 16-bit for example. But if we want to generate a .map file for the linker, a linker map, we can look at that, and that says sort of either what the linker is going to put in certain sections, or what the linker did put at those sections. I don't remember if this is more of an input or output, or if it's just info and it doesn't get processed. But if we compare like the boot map file to the boot linker script, we can just compare and contrast that I am putting the text section at 7C, so that's good. It's, I guess, FB in length. We're padding out, or Clang is padding out to this position, I guess, to either look nicer or be better for the processor to run, better alignment for cache or something. We get some program linkage and global offset tables, which don't show up in the final flat binary, but I guess they were there with the 0 length from the object file. Then we have RO data that is coming after text. We have an interpreter section, which I shouldn't be using. GNU specific versioning, dynamic symbols and strings, the hash value, EH frame, which I don't like and get errors over, so I don't generate it with asynchronous unwind tables. That compiler flag. Data's after there. Some dynamic section, more global offset and program linkage tables for data. Probably for symbol maps and such. And the BSS and common, which common is usually like initialized or uninitialized global data that it puts that doesn't normally go into BSS. I guess BSS would be 0 initialized, common would be uninitialized maybe, for some reason. But those usually go together, so I've been sticking them together. Dynamic BSS and the boot signature, that does go at 70FE, it is 2 bytes in length. That linker command is short A55. It discards these. And it looks like it puts all the debug info at the end, but the address is 0. Well, if it's coming from the object file, that's true, but they do have a length, and I don't want those in the final binary, so I'm stripping them out, but object copy may not add that by default for a binary output. I'm not sure, but I am being explicit with that in the makefile to strip that. But that can be useful to look at. If you want to compare and contrast with what the linker's actually doing to debug some stuff, it can be very handy. But also mentioning debug, I just want to revert to not have those extra files right now. And I don't. Okay, but also mentioning debug, since I am starting up with the capital S, lowercase s, and running GDB here, I found it's a lot easier than print debugging to use an actual debugger with stuff, especially for low level or bare metal projects that are freestanding like this. I do have a GDB init file, which is just commands that GDB runs when you call GDB, if it's in the local directory. So since qemu starts up with the -s, waiting for GDB on port 1234. You can connect to it with GDB with the target remote localhost 1234. For flat binaries, for ELFs it may be different, but for flat binaries here, I don't necessarily have all these symbols that I need for debugging, so I'm adding as symbol files the ELF things here so that they have these symbols and they have the addresses linked in where they're supposed to be at. Then I'm adding breakpoints at my entry point functions specifically. You could add them at, I guess, line numbers or other function names. But for this example, I'm setting breakpoints at boot, stage 2, and kmain, which are my entry point functions in my C files. I'm doing a text UI layout with C on the top and assembly below that, and then I'm running continue because qemu invoked with the -S flag waits for a continue signal, and that makes it start. So what happens is it loads the symbols, it starts qemu, and it breaks at the boot sector, the first breakpoint there. And for make debug, I'm running the qemu, and then I'm running GDB automatically, so I get this nice startup to where it waits at the first breakpoint at my entry point, which is very nice. So you can use qemu and GDB at the same time in here. You're not limited. Although if the CPU is fully halted, then you'll have to use qemu only and you can't use GDB. That's annoying. The other annoying thing is for stuff like the BIOS interrupts, and I'll just do step to go one C line at a time. Or SI, or step I goes one assembly line at a time, and then just press enter to continue. But if I go to where I get to the BIOS interrupt for 13 here, that's all in like SEA BIOS, C BIOS, or other code like in qemu. I don't have the symbols or the source for that, or I would add it and use it, but I don't have that, so I don't know where I'm at. If you're lucky, list will work if you're not in some weird function it doesn't know the boundaries for. If you're not lucky, then you can, well, you just have to kind of try and remember where you were at and list, like, for example, the function that you were at to get back to a file to be able to lay other breakpoints and go on. So I'll break at line 32 here and continue to there. And I'll go to stage 2. Otherwise I could do continue to go to the next breakpoint, but that's easy enough. You can step by line with C. Next we'll step over, step will go into, but one line of C code generally, and step I will go one line of assembly instruction here. So that's useful. I'll go back to where I was. I'll just continue to where my last breakpoint is in the kernel. And this one will just step because I don't have any BIOS interrupts. I'm just writing to a memory pointer. So I want to print the value of P, for example. P is currently at 14C offset from B8000. This says /A because all the bytes written are going to be for basically blank, or the character data, which is 07, which is the A or ASCII bell flag, I think. Yeah, 0 black background, 7 for white, for a light gray foreground, and that makes a /A, so that's kind of funny. But yeah, other than that, it's a lot easier doing GDB or qemu debugging with this and seeing the code at the same time. An actual debugging experience, not the best, of course, but it's a lot better than trying to printf debug things for bare metal or using a UART or something. But okay, so, you know, print x, print y, they're initialized to 0 and 2, for example, where I'm printing the string at here. You can see vidmem still B8000, but I'll just step through. We can see this slowly print. I can't make this bigger, unfortunately. Maybe I could zoom in. I can zoom in a little, Control-Alt+. Okay. Just to show it a little bit better here, where I'm printing one character at a time. And just hold enter and get that. But when I stop, when it's halted at the end, where I have the, yeah, and see if I scroll, I have to reset GDB with Control-L. That's another annoying thing. But if I'm halting here, I can't use GDB. It doesn't take any input. So that's even if I press enter. So I have to go into qemu and continue or do what you have, but I'll say, okay, well, it reached this point. I'll just quit. That's all right. It does take some of the stuff you typed in and just can't run it at the time. But that's all right. Then I'll escape and I'll say, okay, GDB init, the commands that it ran. It started, it waited at an address. When I connected to qemu, it was just waiting at the reset vector is what that is in x86. Then I added the symbol tables, I added the breakpoints, and then I'd hit continue so it did the breakpoint initially. So those correspond with the commands that I ran here. It's just showing that as output. But okay, that's all I have for this example because I'm running out of breath and I'm talking too much. Tried to make it a little bit faster on my sort of lunch hour that I'm on. So hopefully that explains a bit about just a basic, quote-unquote, contrived example for 16-bit real mode with C, and hopefully more of a practical example here. Even though I'm not doing much but printing, you can invoke BIOS interrupts and work with 16-bit real mode in C with that -M16 flag, if not else the .code16 GCC directive in the assembly output. So I only need a C compiler in make to make low-level projects now. I can work with 16-bit real mode, 32-bit protected mode, 64-bit long mode, if not with UEFI, all just with the C compiler, even though it does invoke and call most likely separate functions for different things, like the assembler. I'm not directly invoking it, so it's a little easier for me, a little more ergonomic. That was my purpose for this, and I thought it was interesting. So hopefully that was a little bit informing or helped you out a little bit. Thank you for watching. Greatly appreciate it. If you want to see more anachronistic things like using C23 where it's not supposed to be used, making 16-bit real mode code with a standard made 1 or 2 years ago is kind of funny to me. I don't know. Anyway, if you want to see more anachronistic things, I'll be working on another project here soon, and you can stop by again if you want to see that. So thanks for watching, and I'll see you then.